Hi, my name is Julia Silge, and I'm a data scientist and software engineer at our studio. And today, in this week's screencast, we are going to use last week's Tidy Tuesday dataset on human-computer interactions from Star Trek. And we're going to train a model to use the text of the interaction to distinguish between whether a person spoke the interaction or the computer spoke the interaction. So we're going to try a couple of different feature engineering approaches, a couple of different models, and we're going to use workflow sets to test them on our resamples and see which one turns out best. All right, let's learn about talking to computers. Do you think if I talked to my computer right now, it would be able to tell me, do anything useful? I guess I am talking to my computer right now. Actually, now that we think about it, I'm having a moment. All right, so this data set, which if you're gonna watch this right when I publish it, is actually from last week's Tidy Tuesday, is a data set of interactions between people and computers from Star Trek. It has a lot of really great, a lot of really fantastic, different kinds of data here, different variables. I'm going to focus on this character type variable here, which is like person, computer, and that's who speaks the text, the interaction. And we have the interaction here in this column. Notice that they're not, sometimes they are one time in this, and sometimes they are they're in these multiple times. And the reason why sometimes they're in here multiple times is because, for example, they are it's in a tidy format where if there's two types on it, it is in here twice. So, if the observation we're interested in is type, we have one row for each of those. So the value ID here is what would let us only get each of these once. And since we're only interested in interaction and character type, we only want each of those one time. So to start with, let's take this raw data. Let's do distinct value ID, and so if we keep all of these, so that cuts down, on the data quite a bit because these are duplicated a lot. So this is actually not that big of a data set, but we're going to see if we can do some machine learning with it anyway. So this is a pretty tiny data set, so just keep that in mind as you look at the rest of this. This is, basically almost to the point of being a toy data set, but it's pretty fun, so I think it's still worth walking through and seeing what is it that we can learn from it. You can check out the Tidy Tuesday hashtag to see some, really nice examples of EDA. I'm just going to make one exploratory plot and look at using tidylow, which is a package for computing weighted log odds. I am going to look at what words have a higher log odds of coming from the computer and what words have a higher log odds of coming from the person. So I'm just going to do that one time. So I'm going to say computer raw. I'm going to do the same thing here. And then I'm going to tidy the text. So I'm going to tokenize and tidy it into Word from interaction. And then I will count by, computer versus person, word, and let's say sort equals true. So I see the most common words at the top. Let's call this computer counts, like this. So now this is the counts. So person says computer a lot, and then we've got, very common words like V2NA. Let's now let's compute the log odds. So we say the set here and then the feature. So the set here is the person versus computer. The feature is the word. And then N for what has the counts. For us, that is in fact N. Like that. Fantastic. I think if I do that again, I bet, yeah, some of these have very low counts. So, and I'm not really interested in those. So let's filter at least N is greater than 10, like that. That looks pretty good. And then let's take, well, actually that's only 31. Well, let's do this anyway. Okay, so for each character type, let's take the top. Let's do slice max by log odds weighted N equals 10. So we are going to, we're saying for the computer and the person, what are the highest log odds, weighted log odds words for both of these? And we can just pipe that straight into a plot. So let's put log odds weighted on the X. Let's put word on the Y. Let's make fill equals character type. And let's facet by character type like this. I think they'll have different words on these two. So let's start like this. Okay, so these are just in alphabetical order here. So I don't think, labs, we need to tell people that that is a word. I think it's obvious. And then if we say fact reorder word by log odds weighted like that. Okay, nice. So these are the highest weighted log odds words coming from the computer. Seconds in no 24, 5. So a lot of numbers and U and for the person, it's the word computer. So saying computer, and then words like I and me. Notice the computer doesn't say I and me. And program. And notice that there are stop words in these lists, but they are different stop words. So one thing when you do text analysis, you probably, if you've worked on it a little bit, you probably notice that people often are like, oh, take out those stop words, but stop words often hold quite a bit of information. And this is an example where we see that just right off the bat. So I think we're going to explore that a little bit in this set of models. Before we get going with our modeling, let's do our what we will call our spending our data budget. And here we have got, just a tiny amount of data. So we can only there's not a ton for us to do here. I'm gonna keep like more than the default amount of data for training here, which means we have less for testing, but that's life, right? And let's do stratified resampling. Let's call this the comp split. So I'm splitting this data into training and testing right here. So these lines set up the data that I am using for testing and training. So the person saying Battle Bridge, the computer saying Lieutenant Commander data now located in holodeck area 4J, so the computer says you and the person says me and I, which and these are stop words, right? But like these stop words often have a lot of information. Okay, so this we'll split this data into training and testing, this tiny amount of data. And then let's make a training from that split, comp split. We'll get training, testing, and then let's make some resampling folds. We definitely need that. We've got such a tiny amount of data. We'll use bootstraps because it's so small. And Let's do that. Okay, and let's see how this turned out. Okay, so this is so tiny, but I mean, it is what it is, right? This is just basically a very small toy data set. So for each resample, we are going to train on just this tiny number of observations, and then evaluate on this number of observations. So we have now set up our data budget. We have a certain amount of data. We have to decide how to spend it. That's what we just did. Now let's set up some pre-processing recipes. So I'm actually going to make a bunch right now because I'm interested in, hey, what happens if I keep stop words and don't keep stop words? Now, this isn't something that you can really test via the tuning infrastructure that we have in tidymodels, but it is something that we can test via what we call workflow sets. So I'm going to make different workflow sets, and then I am going to use resampling to test them all, and then see what worked best. So let's make my first recipe. So I'm gonna explain that character type via the interaction, and let's call it data equals comp train like this. I have to tokenize. Well, let me load these. So I'm gonna tokenize the interaction. I'm going to do a token filter, and gosh, what am I going to do? I only have 300 rows that I'm training on here. Gosh, let's make it like 80. So that's how many columns we're going to have in our, like in the numeric matrix is going to end up being used for training. And then let's say step TF, let's use TF-IDF. On the interaction, like so. Okay, so that's the first recipe. I'm going to use a couple of models. I think that normalization might help. So let's take this and let's say step normalize all predictors, like that. Let's call that rec all norm, and then let's do step smote, because this we did have an imbalanced data set. If you remember, here there were more examples of the person talking than the computer talking. So let's try to balance that using smote. Let's call that rec all smote, like that. Okay, and just to make sure this works, let's just prep it. And so that ran it. We can see the output by baking it. So that'll give us back the training data here. So this is what we get. Those are so long I can't really see them. Analysis and any at B, begin, bridge, by. So there's 80 columns and this many rows in the training data there. And it's normalized, and so that's why these are all, these are like, that's why we have all these numbers the way it is. Okay, so this is without stop words being taken out. And so let's copy all this, paste it, and let's call this recipe stop. And stop words should be taken out here. Like that. And then let's make this recipe stop norm, recipe stop smote, recipe stop norm, and let's make sure that runs. And let's look at what that output is. I don't need to prep this to use it in workflowsets. The reason I'm prepping it is to make sure that the recipe runs without errors. It's for like checking. And notice here, these are the stop words are gone. Begin, captain, current, Dex, Brahms. Boy, I don't know. 80? Maybe I should go down to 50 if Brahms is in here. I don't know. I'll keep it like this for now, but maybe we should only keep the top 50 words if Brahms is in there. Man. Okay. Let's do, so I know I want to use a linear model as a linear support vector machine. Support vector machines often work well for text models. They are a good option if you are, starting out with a there we go. Okay, so linear support vector machines often work well with text data, and a linear one, like, I don't know if we're gonna be able to learn any nonlinear structure with this little data, so I think this is a good option of what to do here. And then the other thing I want to try is a naive Bayes model. I should have probably loaded this up earlier. So naive, whoops, let me load this. So naive Bayes, and I'm going to set the mode, same mode, classification, and the set engine, it's naive Bayes, like that. Okay, so call this NB spec. And naive Bayes is something else that works pretty well with when you have a lot of features. I don't know, do we have a lot of features here or not? I'm not sure, but naive Bayes often works as a good first option with text data because of the way that handles having a lot of features. All right, now it's time for us to make a workflow set. So we're going to try all of those recipes with all of those models. So let's make a workflow set. So we're going to say our preprocessors, it's a list, so we make it a named list. Let's say all equals rec all norm equals rec all norm, like that. All smote equals rec all smote. And then let's do it the other way. So we'll add all these. Stop norm, and the last one, so we've got, so these, it's not clear to me ahead of time which one of these will work better with this particular set of data. So I'm going to try all of them and see which ones do, because this, it's not that much data. I don't know what's going to work better. Should I normalize? Normally support vector machines really need it, but all my data is already just TF-IDF, so that's kind of already on the same scale. It's already basically normalized. So that's why I'm trying all these things, because I don't know ahead of time what's going to be best. Let's call this comp models, computer models. Okay. So what does this look like? So we've got a workflow ID here that tells us what's in here, and the info is in here. This is where, this is. And so what we're going to do here is we are going to set up fitting these. Let me do it like this. So do parallel. And then I'm going to take the comp models, and I'm going to use this function called workflow map. So you can think of it as analogous to PERS map, where we're going to map over all of these workflows. Start with this one, start with this one, start with this one. And the first we have piped in what we're going to map over. And then the next thing that we put in here is the function that we are going to map over with. We got to put it in quotes like this. So none of these models really have important tuning parameters. So I'm just going to use fit resamples. The resamples that I'm fitting over are those folds I made. And then I'm going to set the metrics because that linear SVM only does hard class probabilities. It doesn't do I'm sorry, it only does hard class predictions. It does not do probabilities. So I can't do any metrics that require probabilities. Computer RS. So for computer result, whoops, shoot. Stop. That's not what I wanted to do. Okay. Okay. I mean, let me make sure. I'm gonna rerun everything ahead. Okay, there we go. So now I'm gonna start this. So remember, there were a lot of resamples, 25 folds. They're super tiny, each one. But what is happening right here now is I have 12 workflows. There's 6 times 2 different combinations of the workflows. And so we're fitting these 6 workflows to these 25 resamples, and then we're going to see how it does. How does it do on all these different workflows using these metrics? So a difference between like fit resamples or tune grid is that we can't tune over something that is all in the same, can be captured like as the same model or the same pre-processing approach. Like these are quite different pre-processing approaches. These are quite different models, and workflowsets lets us set up a way to fluently compare those. So we did it, and now we can since this data is so tiny, and and none of those were super complex models, we got it done. So we can look at this. Let's see how it turned out. All right, let's zoom in so we can see this a little bit better. All right, okay, so first of all, it's not great. Perhaps unsurprisingly, on this tiny toy data set with these pretty simple models, is not fantastic. The accuracy is at best, point, I don't know, it's about 0.7 or something like that, or 6, almost 0.7, something like that. But looking at accuracy is a pretty interesting pattern. The support vector machine did way better than the naive Bayes model. If we look over here, when it comes to specificity, which is probably, I guess that's recognizing the computer, they're a little bit all over the place, but they kind of did about the same. Or is that recognizing the person? We'll know in a minute when we look at some of these results. Where for sensitivity, the SVM did a lot better than the naive Bayes. So they both did about the same for the, I guess the naive Bayes, for some of them at least, did better than the others. Than the SVM, but the SVM did much better on sensitivity than the naive Bayes. So let's look at this in a little, I'll keep this up so we can look at it, and let's look, there's a function called rank results. Where we have all these results here, and let me just look at, let's just look at the accuracy here. Okay, so it looks like that first one, just that plain all SVM is this best option up here. Then normalizing is worse. Then removing the stop words is a little worse. Then notice this is the one with the smote, and that is 1, 2, 3, 4, and that is pretty interesting because look at the fourth one, the sensitivity bumps up 1, 2, 3, and the specificity bumps down, so that they're more balanced. We do a better job of recognizing both the positive and the negative classes. So you can see that here when we balance the classes in the training data, we do a better job of recognizing positive and negative here. It hurts us in overall accuracy, but we do a better job of on sensitivity, and a worse job, of course, in specificity, because that's how the cookie crumbles here. notice that we don't really get into the naive Bayes ones until, you know, down here at 7. They're much worse. So this gives us a pretty detailed view of what's going on here. And you know, there's a lot more we can dig into here, and you know, depending on what metrics are most important to your particular use case, you can really decide which one is right for you. Let us say that we want to just maximize, we want the best overall accuracy. So we'll use that recipe all, you know, with the stop words, and that including, you know, like not removing them, keeping them, not taking them out. And let's use that SVM model. Let's call this computer workflow. And then let us do last fit on it. So we'll take the computer workflow, we'll fit it to the split, and we will take these same metrics because we have that same issue, or the support vector machine cannot handle metrics that are about probabilities, class probabilities. Okay, it's fit, it's done. That's one good thing about tiny toy data, right? Super fast. Let's collect metrics on this and see what we get here. So this is about what we had, you know, on all our resamples. So that's good. And now we can collect predictions from that. These are, remember, predictions on that training data. So it's very super tiny, right? But as we just get close to the end here, so we can say character type, that's the true. The true values are in this column, and then the predicted values are in this column. So you can see it was, okay, so truth is over here. So it was easy to find the people because they were saying things like computer and I and me, and it's hard to find the computer. It's harder to find the interactions that were by the computer. All right, there's one more thing we want to do before we get to the end. So this is a linear model. So we can go and just look at the, you know, like it's kind of a mess here, but this thing that I've taken out right now is a workflow that you can save and predict from later. Like you can use it to, it's a fitted workflow, so you can use it to predict later. But we also can tidy it. And that means we have, it's a linear model, so it just has, you know, for every term in the model, we have a value for how does it push the model positive or negative. So let's make a quick visualization. So for whether it pushes the probability up or down, let's take the top 10 terms in effect size. Ugh, can't type or talk. And then let's remove this for our plot like that. And then let's put estimate on the x-axis, term on the y-axis. Let's say fill estimate, whether it's, you know, positive or negative. What does it push? Does it push the probability in the positive or negative side? And then let's do geom call, like so. Okay, fact reorder term estimate. Nice. Okay. Labs. Why we don't need that. And I think it's here. Scale, fill, discrete, and we can say labels, and we can say, okay. So, which one comes first? I think people. And if we say fill equals more from, like that. Okay, yeah, I did it right. I did it right. Okay. So this is the coefficients from the linear SVM. And so more from people, what pushes the probability more towards people is the interaction having the word computer, any, I, me, this, a, all. So notice these are stop words, but these are the biggest effect size words, things like I, me, and of course, computer. On the computer side, the biggest effect size words are enter, buy, enterprise, failure, seconds, 10, dex, 5, will. So a lot of these are stop words too. So this is a really great example of a situation where stop words carry a lot of meaning. All right, I think this is a great opportunity to see in what kind of situation you would use workflow sets when you have a couple of different feature engineering approaches that you want to be able to try, maybe a couple of different models that you want to be able to try, and you don't have information about which one is going to work out better. So you need to be able to, in a principled way that adheres to good statistical practice, be able to try out multiple of them and see what works out best. I think is a particularly interesting example because stop words, we think of them as like, oh, yep, just throw them out, or think of them as like no information words or low information words. But there are multiple situations in which actually they carry a high degree of information, or in fact, they can be the most informative words. So I hope this was helpful, and I'll see you next time.